battle between fire and ice, a world where lava lakes shine more intensely than any volcano on Earth, while frozen sulfur falls like toxic snow over a constantly shifting landscape. There, the surface never rests, and millions of kilometers away, scientists on Earth are only beginning to unravel the invisible forces driving this colossal chaos. It is not the sun that fuels this fury, but gravity, a brutal dance between Io and Jupiter, where cosmic tides compress, stretch, and heat the moon's interior until rocks melt and explode in gigantic eruptions. What appears to be destruction is, in fact, physics in action, and every explosion reveals a secret about how worlds are shaped across the universe. Io is not just an ordinary moon orbiting Jupiter. It is a world in constant eruption, where the surface never remains the same for long. Every region of that celestial body is sculpted by invisible forces that never cease, transforming solid rock into incandescent rivers of molten material, while Europa hides an ocean beneath a thick crust of ice, preserving a cold and silent environment. Io lives at the opposite extreme. There, fire reigns, lava lakes glow intensely against a dark sky, permanently illuminated by Jupiter's colossal reflection dominating much of the horizon. Discovered by Galileo Galilei in 1610, Io was one of the first moons identified orbiting another planet. For centuries, it remained only a point of light, observed through increasingly advanced telescopes, revealing nothing of the secrets hidden beneath its modest appearance. Only in the 20th century, with the rise of space exploration, did its true nature begin to emerge. Science finally gained the opportunity to observe Io up close, and what it found surpassed every expectation. It was the Voyager 1 probe, in 1979, that recorded the first clear evidence of active volcanic eruptions beyond Earth. Images sent back to our planet showed gigantic plumes rising high above the surface, marking humanity's first observation of volcanism on another world. That discovery permanently changed planetary science. Until then, scientists believed small celestial bodies cooled quickly after formation. Io proved that internal forces could sustain intense geological activity for billions of years. Today, we know that Io hosts more than 400 identified active volcanoes, making it the most volcanically active body in the solar system. Not even Earth, with its complex tectonic systems, reaches the same density of simultaneous eruptions. But what fuels this extreme geological violence? The answer lies in Jupiter's colossal gravity. Io orbits so close to the gas giant that it undergoes constant deformation caused by overwhelming gravitational forces. This process is known as tidal heating. As Io moves along its slightly elliptical orbit, it is repeatedly squeezed and stretched. That continuous flexing generates enormous internal friction. The heat produced is sufficient to maintain vast magma reservoirs beneath the crust. With each completed orbit, Io is literally deformed like an elastic sphere under immense pressure. The result is a constant buildup of thermal energy within the moon's interior. Lava temperatures can exceed 1,600 degrees Celsius, and some studies suggest even higher temperatures in certain regions. Such extreme heat indicates magma compositions potentially different from most terrestrial volcanoes. Eruptions launch plumes reaching hundreds of kilometers in altitude, some rising over 400 kilometers above the surface. These plumes form immense arcs of material that later fall back as sulfur-rich particle rain. Sulfur and sulfur dioxide spread across the terrain, painting the landscape in vibrant colors. Intense yellows, deep reds, burnt oranges, and pale white patches make Io one of the most visually striking worlds in the solar system. More recently, NASA's Juno mission performed extremely close flybys of Io. Its instruments captured unprecedented high-resolution images, revealing details never seen so clearly before. One of the most remarkable findings was the detection of a massive eruption, considered among the largest ever recorded on the Moon. The region covered by newly solidified lava spanned tens of thousands of square kilometers. In comparison, that scale surpasses many historical volcanic events on Earth in both extent and thermal output. Infrared sensors also detected extremely hot spots scattered across the crust. These hotspots indicate constant subsurface activity, even in areas that appear stable at first glance. Such data support the hypothesis that Io may contain a partially molten global magma ocean beneath its crust. Unlike Europa's subsurface ocean of water, Io's would consist of molten rock. Computer models suggest this magma ocean is not entirely uniform. It may be concentrated in deep layers interacting with more solid mantle regions. Another crucial factor is the gravitational influence of neighboring moons, Europa and Ganymede. They participate in an orbital resonance known as the Laplace resonance. This resonance keeps Io's orbits slightly eccentric rather than perfectly circular. That small orbital eccentricity is essential for maintaining continuous tidal heating. Without this triple gravitational interaction, Io would likely have cooled much faster over solar system history. Io's interaction with Jupiter's enormous magnetic field produces extraordinary phenomena. As it moves through that intense magnetic environment, Io generates a powerful electric current. This current forms a magnetic flux tube connecting Io and Jupiter. The result is spectacular auroras appearing near Jupiter's poles. It is a complex gravitational and electromagnetic dance that makes Io an active participant in Jupiter's magnetosphere. Io's atmosphere is extremely thin and composed mainly of sulfur dioxide. During major eruptions, that atmosphere temporarily becomes denser. When Io passes into Jupiter's shadow, temperatures drop dramatically. Part of the sulfur dioxide freezes and settles onto the surface as volatile frost. Once sunlight returns, the frozen material sublimates back into gas. It is literally a continuous battle between fire and ice on a planetary scale. Scientists believe studying Io helps us understand the early stages of rocky planet formation. Tidal heating may have played a major role in the thermal evolution of young planetary bodies. Io offers a natural laboratory for studying extreme geological processes impossible to replicate on Earth. Impact craters are rare on Io because lava flows constantly renew the surface. This indicates that its crust is geologically young. Constant resurfacing erases ancient records, complicating reconstruction of its earliest history. Studying Io also aids our understanding of exoplanets orbiting very close to their stars. Some of these lava worlds may experience tidal heating similar to Io's. Modern spectroscopy allows scientists to analyze the chemical composition of eruptions. These analyses reveal complex sulfur compounds and traces of molten silicates. The abundance of sulfur explains the moon's striking coloration and influences its atmospheric dynamics. Io is often described as the inferno of the solar system. Beyond dramatic imagery, it represents an extraordinary scientific achievement. Each space mission deepens our understanding of gravitational interactions and orbital physics. The same physics governing Io applies to icy moons, close-in exoplanets, and distant planetary systems. Understanding Io means understanding how gravitational energy can shape entire worlds. It demonstrates that geological activity does not depend solely on proximity to the Sun. Despite receiving relatively little solar energy compared to Earth, Io releases tremendous internal heat. This proves gravitational forces can rival stellar radiation as a planetary energy source. Each new discovery on Io redefines what we consider possible within the solar system. Even centuries after its discovery, Io continues to reveal astonishing secrets. Data from Voyager, Galileo, and Juno combine to create an increasingly detailed portrait of this extreme world. Future missions may focus even more closely on Io and its interaction with Jupiter. Exploring this moon helps us better understand planetary diversity and universal physical mechanisms. Io reminds us that the cosmos is dynamic, violent, and extraordinarily complex. As we observe its eruptions from afar, we deepen our understanding of the fundamental forces shaping the universe. Science does not turn Io into myth. It transforms Io into measurable knowledge, grounded in data, models, and rigorous observation. Every active volcano is visible evidence of gravity at work. Every lava flow is the thermal signature of an invisible orbital dance. Io is not merely a spectacular visual phenomenon. It is a living lesson in astrophysics, geology, and gravitational dynamics. The more we learn about it, the more we realize the solar system still holds astonishing phenomena. Io proves that even relatively small worlds can possess gigantic stories. It challenges simplistic theories and demands increasingly sophisticated scientific models. The battle between fire and ice continues every day on that distant moon. Here on Earth, scientists continue observing, calculating, and analyzing each new piece of incoming data. Apparent chaos follows strict and predictable mathematical patterns. Within the balance between destruction and renewal, Io remains one of the most fascinating worlds ever studied. If you want to keep exploring extreme worlds like Io, based on real science and the latest discoveries from NASA, this is your place. Subscribe to the channel, activate notifications, and follow every new revelation about the secrets of the universe. Because out there, between cosmic volcanoes and gravitational storms, the cosmos continues writing its story, and we are only beginning to understand its most astonishing chapters.